as we move on to question 11. Okay. So we have for question 11 here. All right. Ammonia NH3 is a weak base with a Kb value of 1.8 times 10 to the negative 5. Okay. So let's just write it down. Ammonia is a weak base with Kb of 1.8 times 10 to the negative 5. What is a pH? And percent ionization. So for this, we actually need to go through step by step to be able to find this and use certain things to be able to put the whole picture together. The first thing we need to understand about ammonia is how it actually reacts with water to be the weak base as it says it is in this question. Okay, so we actually write down our equation. That would be NH3, aqueous solution or gas, but most likely aqueous solution to actually mix with the water, plus H2O, liquid, turns into NH4 plus aqueous plus OH minus. So here you should be able to see that one of the hydrogens from the H2O moved and attached instead to the nitrogen or the ammonia instead. So with that being said, okay, our formula that we're going to use in regards to Ka, well Kb actually, because we're dealing with the OH, so we're actually going to use Kb, but it's actually very similar to Ka, but it just says Kb is still products over reactants, but you have to make sure that you're solving for the concentration of hydroxide ions, and that will be the key difference there. So Kb is products over reactants, and we still do not count water because water is just the solution it's in. Okay, it's just like the liquid component. It's not factored in here. Think of it like almost like being an excess. Actually, even better. Yeah, actually, excess would be a good way to put it, to where it's just not considered because it does interact. It is part of the reaction, but it just like what the NH3 is submerged in. Okay. So that's the first formula we need. And in order to solve through this, we actually need our oh wait, we can actually solve for the percent ionization first, actually, because the way the percent ionization works is that it's by, I'm trying to remember, because the percent ionization is used to find the Kb. So exactly, it would be, yep, okay, it would be pretty much how much of the NH3 actually separated to the NH4 and OH minus. So we can actually kill two birds with one stone here, because we're going to use is the ice table. Okay, so with that being said, ice tables are initial change equilibrium, and we have to do this for each of the components that actually are factored in the Kb equation. So it's going to be the NH3, that's the OH minus, or actually let's start with the NH4 plus and OH minus. So the initial is that we actually put, think of it as we just put straight up just ammonia, okay? And as they said in this question, it's pH of 0.0390 moles. So we know we have this 0.0390 moles in terms of the concentration, okay, moles per liter. And that means because we put that there, we actually start with 0 for these two. So now for the change, we're saying that for every ammonia, it's going to produce, I guess for every mole of ammonia used up, it's going to use 1 mole of this, and it's going to produce 1 mole of the ammonium ions and the hydroxide ions. So that's why you just say minus x plus x plus x, okay? And the equilibrium is going to be now 0.390 minus x, and it's going to be just x and x. So now factoring that back into our KB equation, okay? We're going to get that KB is equal to, all right, x squared at the top over 0.390 minus x. Now, what we're going to do is a little bit of a shorthand. We're going to see if, in a sense, the concentration dwarfs the KB value so much to where you don't see a noticeable change in the 0.390 once it actually dissociates. So the way we do that actually is that we want to see if the concentration is at least 1,000 times bigger than our KB value. So we're just going to divide 0.390 divided by 1.8 times 10 to the negative 5. And wow, it is 21,000 times at least bigger than our KB. So with that being said, actually, our shorthand now, our formula just becomes like this. X squared over 0.390. Why? Because what we're saying here is that the change in the concentration of ammonia is going to be so small that we're almost going to round back up to 0.390. That's the assumption we make. So let's now actually do the math. We're going to multiply these two together, 0.390 times KB, and then we're going to square root it to be able to get x. All right? So that means now our x value is going to be, where is it? 0.390 times 1.8 to the power of negative 5, and then the square root of that. So our x value here is 2.65 times 10 to the negative 3. As you can see here, if I did 0.390 minus that, we get 0.387, which frankly isn't the biggest change ever comparatively. That's why. We could have solved this through like the quadratic equation as well, but you notice that the answer we would have gotten is going to be almost as close as well. So rather than just saving us the headache rather than having to go through all those steps. So with that being said, let me just check here in terms of what else we can do. Okay, so now we have our x. So we can actually use this to find our percent ionization. This is pretty much saying that of the concentration of 0.390, 0.265 times 10 to the negative 3 of it was ionized. So our percent, as in, was actually separated. So our percent ionization would be x over that 0.390. Okay, that's a total we have divided by so 0.23. Yep, divided by 0.390. Well, you should get our percent ionization times 100. So just add that. Okay, times 100, and we actually get it is a 0.679% ionization. And now that we've done that, let's use now the rest of the question to actually find out what our pH is. So the way pH will be found, we actually first find our pOH. Because what we've done here is find the concentration of OH minus. This will not give us our pH, but instead it will give us our pOH. But it's still the same formula of pOH is equal to negative log of hydroxide. Okay, so we're going to use that x value again of the 0.00264, etc. So we're going to now do negative log of that answer. And our POH, okay, when we put in the calculator, ends up being 2.577, around there. So to find pH, right, in this case, because 14 is equal to POH plus pH. So if we organize that, pH is equal to, just to make sure I have it correct, 14 minus POH. So 14 minus the answer we just got, the pH was going to be, for this question, 11.423. And so there you have it. We've now been able to give you the not just the percent ionization, but the pH as well. And just to be able to show you in terms of the whole quadratic situation, if we're to do the quadratic formula, I do have it memorized, just like how to approach it. The KB would be your B value. So what we have first, it would be the 1.8 times 10 to the negative 5 squared, okay, times 10 to the negative 5 squared, and it's going to be plus 4 times, or 1 times C. In this case, the C would be the 1.8 times 10 to the negative 5 times the concentration that were given to us, which was 0.390, okay? And then we square root that, okay? And then we would subtract that value from the KB. I mean, it would subtract KB from that value, so that would be minus 1.8 times 10 to the negative 5. Okay, and then we divide that by 2. So the answer I got when I did the quadratic equation, I got 0.264. So as you can see, making that assumption does work. 0.265 versus 0.264, and in fact the 0.265 I had to round up to get there. So the difference was literally like the number after. Like there was quite a very little difference of whether to use a quadratic or not. So with that being said, I'm pretty confident in my answer in terms of how we solve this. So as we go through, they did set up the ice table, and exactly they also dropped their x because it's so negligible, okay? And we showed that because we did the whole comparing if it was 1,000 times greater, the concentration versus the KB. And so the first thing they did was find the pH, which was indeed 11.42, and the percent ionization, okay, was the amount of hydroxide produced versus the total we were dealing with, not just the NH3, because technically the NH3 now is a little bit less, and exactly the percent ionization was 0.68, which is what I got. They just rounded a little bit different. So this is correct. And now question number 12.